So we're going to start the fundamental theorem of algebra. So the generalized form of this can be said as if Px is a polynomial of degree n, then Px has exactly n zeros, each which may be written in the form a plus bi, where a and b are real and some of which may be repeated. So pretty much what this is saying is it's saying if we have this polynomial and it has its leading power is x to the n, so this could be any number, and you know there's all these other terms in here, we can actually break this out into x minus all these factors all the way to x minus, I'm just going to pick a random letter, and there would be n number of factors here, n factors. Now, the factors might be real or they might be imaginary. So what it's saying here is it has n zeros. So if we think about these are our zeros. These are the values of x that would be there, and we can write them all in the form a plus bi. So to break out this more, we've got some more points here. Every real polynomial of degree n can be factorized into n complex linear factors, some of which may be repeated. So I'm just going to go with something like, this just means, what this means is if we had a polynomial, let's just say this polynomial is to degree 3, we could write this as x minus a plus bi, and we could do 3 sets of these factors here. So these aren't the same factor. I'm just trying to put it in to show you that this can be broken up, and we would have one of these would be minus. Anyway, sorry. We can break this up into linear factors that are complex, and they will have the same number as the degree of our thing. I'm just going to erase that because that's not quite right. So I don't want you putting that in your notes. All right. Every real polynomial can be expressed as a product of real linear and real irreducible quadratic factors. So this sort of links in with our next, with this one down here. If we have a 0 of a real polynomial, then its complex conjugate p minus q is also a 0. So the idea being that if we break let's just say our px here up into values, we will have x minus alpha. This will be our real factor, and then we could have x minus p plus qi as one of our zeros, and then our other 0 would also be x minus, and we would have p minus qi there, and they become 2 of our factors there. We have the same amount of zeros as we do degrees. Repeated ones means that purely if we had x minus 2 was a factor, we can still have x minus 2, and that can be a repeated factor. Every real polynomial of degree has at least one real 0. So the idea being if our polynomials have complex conjugate pairs, so if we imagine that if we have a complex root or a complex number as our 0, bi, x minus a minus bi, so I should have used p and q, and if this polynomial is to degree 3, these go in a pair. We can't have a complex one that if it doesn't have a pair, so that means we've got our real factor here. So real, and these are complex down here. I've tried to rip through this because this is just one of those things that this section's almost like purely definitions in this. We're just finding things that can help us in this space. I've got to the example question. Suppose negative 3 plus I is a 0 of this polynomial where a is real, hence find a and all the zeros. So straight off the bat, I can either do what the textbook has done and do the sum and product method, okay, which if we remember, you know, our 2 roots, this has a degree of 3. So we're going to have alpha, let's say alpha is our first root, 3 plus I. Beta is going to be our second root, which will be negative 3 minus I. And then gamma will be our real root. So this will be a real one here. So we could do sum and product, which means we would break into a quadratic factor of x squared minus the sum of the roots, x plus the product. And if I was going to quickly do this, the sum would be adding these two values together. So the sum would equal, I'm just going to write here, the sum of these two roots, I'm just going to avoid this one. The sum of these two would be -6, and the product, which is -3 plus I multiplied -3 plus I, is going to give us 10. All right, so that would be -3 times -3, which gives us +9, and then I times I, negative I squared, which is +1. So this would mean that we have x squared minus -6x plus 10 is one of the products. And then we've got another value here, which would be x, which would be, it would be some constant, let's just say a, times x plus b in that space. Now, conveniently, that will line up. I'm just going to pause here to quickly go through the other method, which would be to go, well, x minus -3 plus I is a root, x minus -3 minus I is a root, and then our final one here is x, I keep forgetting the coefficient, which is poor notation, ax plus b is also a root. Now, if I quickly expand this out here, I get x times x gives me, and let's just change that form like we practiced in class the other day. So I could rewrite this as x plus 3 plus I, x plus 3 minus I. These now become a difference of two squares, so I have x plus 3 squared minus I squared. And then let's make sure we keep carrying this through. Ax plus b, ax plus b. Okay, and this becomes x squared plus 6x plus 9 plus 1 ax plus b, which becomes x squared plus 6x plus 10 ax plus b. All right, now I've got a bit distracted in showing you those methods. Let's come back and grab our thing we're actually meant to be working with. So copy, we need to make these equivalent expressions. So let's just go, there's no negative, that was part of my equal sign. So let's just get rid of that. Okay, so these two forms need to be next to each other. And if we look at this, if we expand this, it's going to work for us, apart from 10 times b is just going to be the constant. So we know here 10 times b has to be 10 times b has to equal -30, just because that's the only value with a constant. Therefore, b will be -3. So let's rewrite this out. X squared plus 6x plus 10 bracket ax take 3 has to equal our polynomial there up here, which we're going to do. So let's expand this. So I'm multiplying everything by this term here, and I'm going to get ax cubed plus 6ax squared plus 10ax. Now I'm going to multiply -3 by all of these terms, so I get -3x squared, -18x take 30. So this has become ax cubed plus 6a minus 3x squared plus 10 minus 10a minus 18x take 30. All right, we've now got to use our polynomial equality. So 6a minus 3 has to equal, so 6a minus 3 is our coefficient of x squared, and then I've lost that somewhere. Did I have that in my original question? I didn't. That is probably confusing. All right, so then our coefficient here is 9, so if I add 3 to both sides, I get 6a equals 12, a equals 6. All right, so 8 does not equal 6, a equals 12 over 6, which equals 2. All right, now we try our other equation, because if this doesn't work, then we're stuffed. So 10a minus 18 equals a. So let's add 18 to both sides and take a from both sides. So 9a equals 18, a equals 18 over 9, which equals 2. Perfect. So big tick, we've got both the same for that. Let's put it back into our equation and see what our factors are. So if I'm going to grab this form here. So copy that and put that down here. This now means that we can remove our a, we're going to put a 2 in there. And so this means here, -3, that one of our factors is 2 to x take 3 equals 0, 2x equals 3, x equals 3 on 2. I'm going to bring this back up here. So our real root here is 3 on 2. And so now we've got 2 complex roots and 1 real root. All right, thanks guys.